Don't give anybody COVID or flu or whatever. All right. So I wish you better. And okay, you can hear me and you can see the screen, right?
Right.
And it's recording, right?
Um, I mean,
There's a little thing on the
yes,
left that's
right. This meeting is being recorded. Right. Thank you.
perfect. Okay, let's get going. All right, last time. What did we do last time? We looked at the relationship between thermodynamics and statistical mechanics. And in particular, we looked at how you can relate thermodynamic functions, such as the isothermal susceptibility, to things that you can compute only in statistical mechanics, such as spatial correlations. And I derived for you a thing called the static susceptibility sum rule that was an exact relationship between the susceptibility and the correlation function. And I gave you a very heuristic argument about the shape and functional form of the correlation function, namely that there's some length scale over which things get correlated, specifically fluctuations. Therefore, if there's a length scale, you might naively expect that the correlation function decays exponentially, and we're going to derive that in the class. And in the homework 2 that you've got, I gave you an exercise where you actually can explicitly compute this using a method which is related to a thing called the transfer matrix. We'll talk about it later in the class. So what that argument showed you was that the correlation function decays exponentially with distance. The susceptibility is a integral of the correlation function. The susceptibility we know diverges as the temperature goes towards the critical temperature, but the correlation function decays exponentially, so the integral of the correlation function over space will also be a convergent integral and so will not diverge. And so we discovered that the only way that we could have a divergent quantity on the left-hand side as t tends to tc, and a convergent quantity on the right-hand side as t tends to tc. The only way you can make those two things be the same is if the thing on the right-hand side, the integral, actually does not converge. And that means that the only way that can happen is if the correlation length itself diverges. And I then said, well, if it's diverging, can we use thermodynamics to tell us how it must diverge? And so at the bottom of the screen on the left, I have the divergent behavior of the susceptibility. And on the right-hand side, I have the integral of the correlation function. And I'm looking at the large distance behavior. So that's the only thing I care about, because that's the thing that determines the convergence of that integral. And then what I derived for you was that the correlation length, after some algebra, change of variables, the correlation length actually must diverge, and it goes as t minus tc over tc to the power minus a half as I go towards tc. So indeed, the correlation length diverges at tc, which means that if I say that the correlation function goes as e to the minus r over xi, xi is equal to infinity, so that asymptotic behavior must be wrong. And in fact, I told you what the correct behavior is without any proof, and that is the thing on the left-hand side of the screen, that actually the two-point correlation function at Tc goes as a power law, and the power law involves a spatial dimension and a new critical exponent, which I called eta. And so then at the end of the lecture, what I showed you is that how this is actually happening is not like the correlation function just magically changed its value as t became tc. What actually happens is that the correlation function for any temperature has the following behavior. At large distances, it behaves exponentially, as shown over here on the left-hand panel. And at small distances, it behaves as a power law, as shown there. And all that happens is as the correlation length increases, what happens is that scale at which you cross over between those two asymptotic forms of the correlation function, that moves to larger and larger distances. And so you're measuring, you choose your distance where you're measuring the correlation function, let's say 10 miles. As I get closer and closer to TC, eventually the correlation length becomes 100 miles. And instead of being where R is much greater than the correlation length, now R is much smaller than the correlation length, and you sample a different regime of the correlation function. And that was shown on these two graphs on the left-hand side. So what I want to talk about today is I'm going to use this to show you now that we understand a little bit about spatial fluctuations, I'm going to talk about how we can work out when mean field theory is adequate. And we're going to find a very interesting answer to this question. And then we're going to construct a sort of improved version of mean field theory, which I would call Landau theory, which I want you to think of as being a coarse-grained, spatially extended description of a system which has been averaged, but averaged up to a certain point, and we will explain the details of that later. All right, so before I get started with today's lecture, is there any question about the material on the left-hand panel from last time? Okay, if anybody has any questions they want to ask me afterwards or in Teams, please go ahead. So what we're going to do today is we're going to follow section 5.7.6 and 6.1 from my book. We're going to derive a criterion which tells us about the breakdown of mean field theory as T tends to TC. So what we're going to find is we're going to see the inevitable breakdown of mean field theory as you get closer and closer to the critical temperature from above and below. And why is it inevitable? We're going to show that mean field theory itself predicts the seeds of its own destruction. The best physical theories are not ones that always give you a good answer, always give you an answer. As an example, take the standard model of particle physics, renormalizability. The standard model of particle physics was constructed during the 1960s and 1970s and 1980s, when people thought that renormalizability, the idea to be able to renormalize quantum field theories, was an important aspect, a fundamental criterion for physical theory. And people used it to derive quantum electrodynamics, to derive the weak interactions, the QCD, and grand unified theories, and so on. But later we learned, as a result of the renormalization group, that renormalizability is not a criterion for physical theories. And the viewpoint of high energy physicists switched from being, this is the ultimate theory of everything, to, oh, this is just some effective theory, kind of like the effective theories that we have in condensed matter physics. So the viewpoints of condensed matter physicists and high energy physicists converged, and this happened in the early to middle 1990s, and so now everybody thinks of these theories that we have, like the electroweak theory, unified theories, field theories, and we think of them as being effective low energy theories of the sort that I'm about to introduce to you today. Now, the thing about these theories is that they tell you when they work and when they don't work. And I'm going to show you an example of that with mean field theory. We're going to literally produce a mean field theory, and then we're going to compute self-consistently when that theory satisfies its own assumptions. And what we're going to find is that as I get closer to TC, the theory actually does not satisfy the assumptions that were built into the theory. Okay, so the theory predicts the seeds of its own destruction. Okay, that you might say, well, that's terrible. That means mean field theory is useless. I say no. What that means is the theory tells you when it breaks down. Imagine that you had a theory of nature that said, here, I will always give you an answer to a question. So I can calculate. I always get a finite answer, so I can calculate. Okay, but you never know whether that answer is correct or not. Okay, that's the problem with theories that don't predict the seeds of their own destruction. So every good theory should be able to predict the regime in which it is an asymptotic approximation to something else. And perhaps by the way that it breaks down, it will tell you something about what is the theory that should supersede it. Okay? Remember how quantum mechanics was discovered. It wasn't discovered by doing quantum mechanics. Quantum mechanics was discovered by doing statistical mechanics. Okay? The black body radiation problem. Brownian, well, I don't know. I'll just leave it like that. But that's how Planck discovered his law, right? It was trying to understand the breakdown of the thermodynamics for the black body radiation problem. Thermodynamics and statistical mechanics is a very powerful theory which supersedes, because it doesn't rely on the underlying nature of matter, as it were. it can tell you things about it that other theories do not do. And so that's why one of the reasons why it is so powerful. So that's how we ended up with quantum mechanics, because of statistical mechanics. Okay, so what we're going to do is we are going to see that there's inevitable breakdown in mean field theory as T tends to Tc, and mean field theory predicts the seeds of its own destruction. And this is a feature, not a bug. We're going to construct a measure of the relative importance of fluctuations. And why are we going to do that? Well, remember that when we introduced mean field theory, we discarded fluctuations about the average value. Okay, and we're going to see, so what we're going to do is we're going to construct a measure of the relative importance of fluctuations. And then what we're going to do is we're going to say, in mean field theory, this measure is assumed small. And we saw that explicitly, but the question we're going to ask, does mean field theory predict it to be small? And there's two answers to that question. There's a yes answer and a no answer. So the yes answer is, then that implies that mean field theory is self-consistent. And if the answer is no, then that means it's not self-consistent. And it will tell you when it breaks down. So that's the idea. So let's get into it. So just to remind you, when we wrote down our derived mean field theory, what we did was we wrote down the Hamiltonian exactly as minus sum over I hi si, and this effective site-dependent field hi was equal to the external field plus the sum over J, Sj, Jij. So that was how we defined it. And then what we did was we wrote down that this can be written as H plus the sum over J, the average of Sj, Jij, plus Jij, Sj minus the average of Sj. That was an exact statement. And then what we did was we neglected that, so we threw that term away. And so the question that we have is then, how big is the neglected term? And the answer is, well, what am I going to compare it with? So the answer is big with respect to what exactly? And the answer is, well, the only thing that makes sense would be the average value of the spin itself. So then we can make a dimensionless measure of this error. So what do we do? Well, so let me tell you what it is, and then tell you what the motivation is. So here is a form for this dimensionless measure. I'm going to rewrite this in a slightly different way later on, but let me just give you the basic idea. We're going to write it as like this: Si, Sj, minus Si Sj, I'm going to look at that thing, divided by Si Sj. Okay, so that is one possible way to construct this object. And this interpretation says, well, what I'm doing is I'm looking at the fluctuation of spin I, the fluctuation of spin j, and then I'm normalizing that by the average value of spin I, and I'm normalizing that by the average value of spin j. So that's really what it is. Now, why do I think of it like this? Well, the reason is as follows. The rationale is that if I'm ignoring fluctuations, then the thing I'm actually interested in is the correlations. So the thing that is hard in statistical mechanics is the term SI, Sj in the Hamiltonian. That term is the term that gives you the interactions. And what we did when we wrote down mean field theory is we wrote that down in mean field theory as Si times the average of Sj. That is roughly what we did in mean field theory. This is a sort of another way to derive it. In other words, what you're saying is this term SI, in the Hamiltonian is the term that stops us being able to factorize the partition function. So in order to do the calculation, what we do is we replace this term, which is like, you tell me I, you tell me J, I tell you what is the appropriate term in the Ising model Hamiltonian. Now we're saying, well, we'll just take Sj, we'll just replace Sj by its average value, and then now it becomes Si times the average of something, and that's really what we did in mean field theory. That's basically why it works. Well, if that's true, then when I calculate the expectation value of Si, Sj, what we are essentially doing is replacing it with Si, Sj. So that's really what we're doing. And so what we're asking for is, well, then, what is the, what we're asking for is what is the fractional error in this approximation? Okay, so that's what we're doing. Now, that's the idea of this object, and the other thing is that this E is dimensionless, and so it tells us how good this approximation is. Now, notice that if you were exactly in mean field theory, that E would be 0. So if it's small, then it is good. So if E is much less than 1, then that means that mean field theory is okay. So that's good. On the other hand, if E turns out to be much larger than 1, then that means that mean field theory breaks down. So that's that's bad. So that's the basic idea. Now, the question that we're going to have to ask is, what should I and J be? And so our answer to that is, well, we're not going to just choose, site 16, site 194. That would be silly. We're going to try to do something as an average. So what we're going to do is, in fact, we're going to average the numerator and denominator over some region defined by a length scale. Let's call that length scale R. Okay, so we're going to just compute the average of this over some length scale. So now the question you should ask is, well, what should be this length scale? So a naive answer might be, you could say, well, these spins, they interact with their nearest neighbors. So why don't we just, average over the length scale, which is the nearest neighbor length scale, the distance between this spin and the neighboring spin. So you might say, the range of interaction. Okay, so do you think that's a good answer or a bad one? Who thinks that's a good answer? So let's suppose I've got spins that are on the nearest neighbor, so nearest neighbor interacting Ising model Hamiltonian. Do you think it's a good idea that we choose our length scale to be the scale of interactions, i.e., one or two lattice spaces? Okay, so I see Z1. No, Ting Ting. Okay, who are you then?
You should actually go.
Well, do you want to add your name to the list? Add your name. It doesn't matter whether you're enrolled. I don't care about that. So I just want to learn all your names. Add your name between. You're next to Gregory. Okay. Anyway, you're shaking. Okay. All right. So anyway, sign your name. Anyway, you're shaking your head that the range of interactions is not a good measure. Why? Anybody else not sign my list? Well, so why were you shaking your head?
Just anything separate by correlation.
Why?
Because we think the correlation that everything is interact.
But you've just said your argument is we should do X because of X.
Yeah.
That's not. So let me explain to you why you're correct to say no, it shouldn't be the range of interactions. But let's think why. What I showed you last time was that the range of correlations increases as you go towards the critical temperature, right? It's not just the range of interactions is always nearest neighbor. That doesn't change as you go towards the critical point. But the range of the correlations increases. We saw that. We saw the correlation length. Remember, that's how we started today's lecture. The correlation length diverged as T minus Tc over Tc to the 1/2. Okay, I'll come to it in a minute. So the thing that is diverging is the range of correlations, which is something different from the range of interactions. The range of interactions is just the range of interactions. All the emergent phenomena are due to spatial correlations. So that's why we choose the range of correlation. So let me say the answer is no. And the reason is that the range of interactions is fixed, but the range of correlations grows as T tends to Tc. So that means that we should be choosing an R that is proportional to the correlation length, which is a function of temperature. Okay? All right, Andrew, you had a question.
I was making clearer the distinction.
Andrew wants to know what is the distinction between the interaction range and the correlation range. Okay, let me answer that very quickly. The interaction is what you build into the Hamiltonian. The nearest neighbor Ising model, this spin interacts with its neighbor. That's just the range of interactions, and that's the beginning of the thought. The correlation length is the thing that comes out when you compute the correlation function. So you compute the correlation function, and I showed you that it has an exponential form. I haven't showed you how to calculate it yet. In the homework 2, you will calculate it. You lead through the steps of exercise 2, you will calculate the correlation length. Okay, and the correlation length is a derived quantity that tells you how correlated degrees of freedom become when for a fixed range of interaction. And that's the thing that diverges.
But the two must be some linked in some sort of.
No, they're not linked. One is because they're only linked by the fact that they have the same dimensions. The lattice spacing has nothing to do with the correlation length. The correlation length can be 1,000,000 miles. The lattice spacing can be 1 angstrom. And that's the whole point. Okay? The range of interactions is different from the range of correlations. We're looking at the range of correlations of the spatial fluctuations. And the interactions just tells you about the interactions between the degrees of freedom. So that's what's built into the Hamiltonian. Okay?
Is
You-
the correlation,
No,
is
no,
the
I mean-
correlation longer than the interaction? Because one is interaction to 2 and 2 is interacting with 3, then 1 and 3 can become correlated because of this chain of interaction.
That's exactly right. That's exactly right. Thank you thank you for saying that. And as you go closer and closer to TC, 1 interacts with 2, 2 interacts with 3, 3 interacts with 4, and that chain of interactions gets longer and longer. So eventually, it's 1 interacts with 100 miles away. Okay, that's the thing that happens. Okay, let's see. I was going to say something else about that. Oh yes, here's another thing. You would say, well, if I'm going to take statistical averages of fluctuating quantities, I would want those quantities to be uncorrelated. Okay, so if I want to average something, I'd say, well, average a bunch of variables, but if those variables are correlated and actually the same, if I average, I choose 10 people in this room and I average your heights, okay, you're all independent. I will get some just bell-shaped curve with some mean height, some standard deviation height. If I take 10 people in this room, but they're all identical twins, if that's possible, okay, they'd all be exactly the same height. They'd be very, very strongly correlated. I would get a completely wrong statistical average for people's heights from that. So the significance of the correlation length is beyond the correlation length, degrees of freedom are independent. But on the scale of distances smaller than the correlation length, the degrees of freedom are highly correlated. And we're going to use that insight later, next lecture, to derive what's called the Kadanoff block spin construction. Okay, so
Length scale is smaller than R.
we're going to average. I'm about to tell you exactly what we're going to average over. Okay, all right. So the first thing is we're going to use a length scale, which you can think of as being the correlation length. Okay, so now there's a trick. There's really 2 tricks, because if you look at the numerator of this thing, that numerator looks like the correlation length. Sorry, I said that completely wrong. Ignore what I just said. That numerator looks like the correlation function. Okay, remember how we derived the correlation function. And most of the contribution to that is going to come from R smaller than the correlation length. So that's the first thing. The second thing is the numerator is just the order parameter squared. So we know what that is. But the thing is this: when I integrate the correlation function over a distance of order psi, because it decays exponentially for R greater than psi, the contribution from the exponential is very small. So then I can replace the numerator by the integral over all the space of the correlation function, and we know what that is because that is the isothermal susceptibility. I'm going to write this down. Okay, so the trick that we're going to use is that the numerator is essentially the integral from 0 to psi of dr r to the d minus 1 2-point correlation function, and because g of r asymptotically for r greater than psi, it goes like e to the minus r over psi. What that means is that the numerator can be replaced by the integral over all of space, dr r to the d minus 1 g of r. And this, I'm writing this down here because this is just d r up to a surface factor. And then this thing we know is the isothermal susceptibility because of the static susceptibility sum rule. So that means then that we can write down our E, our measure, is then the integral over the volume ddr g of r divided by the integral ddr of the order parameter, so that the magnetization squared, and we're going to choose the volume to be the volume that corresponds to the correlation length raised to the dth power. So just to summarize, what we said was the length scale, which is important, is the correlation length. So we'll calculate this over as an integral over the correlation length. We'll integrate the numerator and we'll integrate the denominator to get an average value over the correlation length, and then we'll divide those. And then what we're going to be able to do is we can replace the numerator by the integral as v goes to infinity, integral ddr g of r. That's not going to make much difference. And so then we're going to get that the numerator is equal to the kbtc times the isothermal susceptibility. And the isothermal susceptibility, as we know, goes like t to the gamma. So this goes like kbtc divided by t to the power gamma. Okay, so remember the static susceptibility sum rule told you that the integral chi t is equal to the integral of d dr over a to the d g of r, and then there was a kbt in there, and that kbt goes where? Somewhere. One over kt. Okay. And because we're close to the transition temperature, I've replaced T by Tc. Okay, so I'm going to replace I'm replacing it like that. Okay, so that's I'm so glad Apple upgraded everything. All right, so now let's then work out what E is then. So the numerator of E is equal to kbtc over t to the gamma, and gamma in mean field theory, we computed that was equal to 1. What is the denominator? So the denominator is the integral ddr over the volume, which is psi to the d, of m squared, and m we know is just going as t to the beta. So this is equal to psi to the d times m squared, and m goes as minus t to the power beta, where beta is equal to 1/2 in mean field theory. And so and psi of t goes as t to the minus nu, and nu is equal to 1/2 in mean field theory. And so what then I get is that E is scaling like t to the minus 1 over t to the 1 minus d over 2. If I did it right, that is t to the minus 2 minus d over 2. So that is how our error, evaluated over the correlation length, scales as a function of t. Okay, so let's put a box around this equation because it's a very important equation. And now let's ask ourselves what it means. So the question is this: as t goes to 0, i.e. t tends to tc, what happens to our error? Well, our answer is if the error goes to 0 as t tends to tc, if that happens, then that means that mean field theory is good because the error is small. If the error goes to infinity as t tends to tc, then that means that mean field theory is bad, and that's too bad for mean field theory. So the thing you can see then is the answer depends on the dimension. So let's have a look at what happens. If d is greater than 4, so 2 minus d over 2, let's suppose d is 6 or something, then I've got 2 minus 6 over 2, so that's 2 minus 3, which is minus 1, and then t to the minus 1 is t to the plus 1. So the answer then, you can see, is that if d is a number greater than 4, then e of psi is scaling like a positive power of little t, and that means that e goes to 0. And so that tells us then that for d greater than 4, mean field theory is good as long as d is greater than 4. Okay. On the other hand, if d is less than 4, then e of psi, so just put d is equal to, I don't know, 2. Okay, so 2 minus d over 2 is 2 minus 1. 2 minus 1 is 1. So then e goes as t to the minus 1. And so that means it goes as a negative power, t. And that means that it goes to infinity as t tends to 0. And that means that mean field theory is really bad for d less than 4, and d equals 4 is a special case, a marginal case. So now now this is an amazing conclusion. Because in all of this calculation, we just used the scalings that came from mean field theory. So note that to do this calculation, it used only the scalings from mean field theory, and it predicted the breakdown. And so notice, so that's comment number 1. Comment number 2, so d equals 4 is a special case, and d equals 4 is known as d equals the d u c. UC means not the University of California, it means the upper critical dimension. So what we've discovered is that above 4 dimensions, mean field theory works fine. just as I told you, just as I showed you in the comparison, and below 4 dimensions, it breaks down. Okay, so Dougal? Yeah? No,
I'm Kavya.
you're caviar. Okay. I'm
This
so
is
sorry.
there's a little bit of a digression,
Yes.
but in your calculations, it's not, at least as far as I can tell, it's not inherent that p has to be a positive integer. So what happens if we have like fractal dimensions? Well, is that meaningful to us?
Yes, yes. I mean, here's a formula, and, and D can be extended onto the radius. Yep. And later we will do it. We will literally calculate what happens. Since we know that 4 dimensions, above 4 dimensions, everything is easy. At 4 dimensions, it's some marginal case. So we can say the real world is 4 minus epsilon dimensions. Let's suppose epsilon is 0.01. Okay? We can calculate from 3.99 dimensions. Okay? And then you extend the calculation to 3 dimensions. And that's what people do. So yes, there's not another question. The point is, I'm brainwashing you. The point I'm brainwashing you into thinking is that D is a continual variable. And in fact, my next picture is exactly makes that point. So let me do that. So did I answer your question,
Yes.
Kavya? Right. Okay. So here's a summary. Right. So here I'm going to draw. This is a temperature, and here is the critical temperature. So what we've learned is that there's a regime when I get too close to TC where mean field theory doesn't work, where its own error estimate predicts that it fails. So away from it, over here, bless you. So here, mean field theory is okay, and here, mean field theory is okay. And then in the middle here is a regime where mean field theory is not okay. And the size of this regime depends on dimension. So we could say that this is I don't know, TC plus a new temperature, which I'll call TG, and let's say this is TC minus TG. And so this is a measure of the length scale over which the mean field theory breaks down. And this TG is a continual function of the spatial dimension D, and it goes in the way that we just calculated with this exponent 2 minus D over 2. So that is the picture. So this region here, where mean field theory is not okay, we call this region the critical region. And the other thing I want to say about this region, it depends on the dimension. That's a true thing. But it also, there's a prefactor that we didn't talk about, and the prefactors depend on the microscopic details. So comment number 3, where was I doing my comments? Up here. Comment number 3 is the prefactor in the size of the critical region is not universal. So I'm going to say just something about that very quickly. So comment number 4. So this TG, so this G stands for Ginzburg. And really, this is called, this criterion that we've talked about, this criterion of E being less than or greater than 0 as T tends to TC. This comes from a series of papers by Ginzburg and Levaniuk. Some of those papers they wrote together. Levaniuk, I think, was Ginsberg's student. So there's one paper which they wrote, then there's another paper where Levaniuk signed it on his own, the advisor didn't sign the paper, and there's other papers where Ginsberg signed it as well. And these were all done over a period of time in the early 1960s. So this is usually called the Ginsberg-Levaniuk criterion or Ginsberg criterion in some places. Say it again?
Was that significant?
Greater than or less than. Right. So that's all I want to say about that. In my book, I don't know if I'm going to go through it in class. Can't remember. Let me just say, this is a very important thing. So you can work out how it scales. In my book, I give a series of examples. Like for magnets, you can show that this thing is easily measurable. Okay. If you look at superconductors, and classic superconductors, you can show that this thing depends on the microscopic range of interactions, the correlation length far away from the critical point. It goes like that to the 1 inverse 6th power, at least in 3 dimensions. So that means that in superconductors, in most superconductors, they behave just like mean field theory. Virtually everything you know in superconductivity, you can get from mean field theory. There's one exception to that, a very important exception, especially important for me. During the discovery of the high temperature superconductors starting in 1986, one of the first things that we learned was that the range of interactions is much smaller in the high temperature superconductors. In a superconductor, you have electrons. Electrons form a bound state in momentum space called a Cooper pair. So 2 electrons, one with spin up, one with spin down, form a composite boson, and that boson then condenses and forms a superfluid, and that's how superconductors work. Okay, all that's discussed in my other emergence and order course. In the high temperature, in normal superconductors, classic superconductors, that length scale is about 1,000 angstroms. In the high temperature superconductors, they're very strongly correlated, and that means that the range of interactions that comes into it is not 1,000 angstroms, it's more like 7 angstroms. Much, much smaller. And the range over which you see fluctuations goes like 1 over the correlation length to the 6th power. You can derive that, it's in my book, okay? And you just do this integral, and you can maybe I'll make it as a homework exercise. It's easy to see. So what that means is in the high temperature superconductors, you get 12 orders of magnitude expansion of the range of critical fluctuations. So in fact, what we did when I was at University of Illinois was we studied the critical behavior of the high temperature superconductors, and for the first time, we were able to measure the fluctuations in 3-dimensional superconductors, and that started a whole new topic in superconductivity, but it comes from looking at this back of the envelope calculation for the range range over which mean field theory works. Okay, so now I'm going to change topics, and the next thing we're going to talk about is a coarse-grained description of the system.
Regarding the average agreement.
You have a doubt. Okay, what's your doubt?
We just discussed that we don't want to average over things that look similar, right? And when we take the correlation length as our length scale, we do know that things are correlated. And the heights example that you had given.
Yes.
So why did we choose our averaging volume to be that of the correlation?
Well, because we're trying to understand, we're trying to understand what is the length scale over which they are correlated, not over which they're not correlated. Right? We're trying to see when the mean field theory is ignoring these correlations of fluctuations. So we're trying to see when those things are important, not when they're not important. That's why we're using language. Okay, so let me talk about the motivation for this section. So what we just learned then, what we just saw was that interacting systems near a critical point become very correlated. And when I say become very correlated, that's really not very good English. What I mean is that they become very work. All right, become very correlated over increasingly large length scales. So what that means is that if I want to have a description of the system, I ought to be able to have a description of the system which says instead of having to deal with all of these microscopic variables, I can replace all of these variables within a correlation length by one variable. So the idea is, here is my system. I've got some correlation volume. Let me draw it like this. So this is meant to be a size of order psi. And because they're correlated in here, our idea is the degrees of freedom are strongly correlated. And so can be considered to be one effective variable. So that is a cartoon picture that we should have in our minds, and this was developed by Kadanoff, Leo Kadanoff, and that's a thing that we'll talk about shortly called the Kadanoff block spin construction. But before we get to that, this insight allows us to now make a somewhat coarse-grained formulation of our statistical mechanics. So that's what we're going to talk about. So let me show you the basic idea. And we talked about this already in the class, and now I'm going to come back to that. So what you'll remember, earlier on we talked about, we have e to the minus beta f, which is the free energy. We have e to the minus beta times the Hamiltonian, and we sum over the degrees of freedom, and that gives us the microscopic behavior. And then I said it would be nice to have a intermediate scale of description where we can then have something separate then that's not the free energy and is not the microscopic free energy. So we're now at the point where we're taking this. We know that this is trace e to the minus beta times our Hamiltonian, and now we want to know what is the intermediate scale of description that goes in here. And what I've already answered for you is what is the characteristic length scale of that. The characteristic length scale of that is going to be of order the correlation length, and we'll see what it is. But the question we want to ask is, what is the effective Hamiltonian governing these degrees of freedom? So let me tell you what the degrees of freedom are, how we construct them. I'm going to give you a cartoon picture, then I'll tell you how to do it mathematically, and then we'll construct this thing. So let's start off with our microscopic picture. So this is microscopic. This is macroscopic, thermodynamic. no spatial variation, and this picture here is intermediate. So let's look at the microscopic scale. So you can imagine I've got my SI. So here is my spatial axis, and then I have a bunch of spins. So I'll just draw something like that, okay? And those are my microscopic spins. So what I want to know is I want to construct a macroscopic variable. So let me call it m lambda of r. And m lambda of r is going to be a function of r. So it's going to live on the same scale here. Now, the SIs, they lived on lattice sites. So these are discrete lattice sites. But now this m of r, this is a continuous variable. And what I'm going to do is I'm going to cause grain. So I know that there is a scale up to the correlation length where things are highly correlated. So what you might say is, well, let's do this. Let's take a let's take some sort of sliding window like this, centered at the point R. And then I'm going to take that sliding window and move it along the R axis. And I'm going to slide that along, count the magnetization inside this region. So I'll call this region of size lambda. And then I'm going to plot what the magnetization in that region looks like. And so I might get a curve. I'll probably draw something that's not quite corresponding to what I'm showing here, but that might look something like that. Right, so something like that. So I do this, I slide this along, and then that produces a continuous variable, which varies in space as shown. So this here is a continuous, sorry, not just it's a continuous variable. And so it's continuous in space, but also m lambda is continuous, and -1 is less than or equal to m lambda of r is less than or equal to +1. So by doing this, I've smoothed in space and I've smoothed the variable. And how might I have done that? Well, what I would do if I take this procedure, cartoon procedure, and write it down mathematically, what I'm basically doing is I'm taking my spins, I'm multiplying them by some kernel, let's say a Gaussian. I'm dividing by 2 lambda squared, and then I'm integrating this over 2 pi lambda squared to the power d over 2, and then integrated dd rj. And then I sum this over j. So that is a way where I take some kernel, I average the spins locally, I sum of all the spins, the kernel dies down, but the spins are a long way away, so that doesn't matter. And then I just slide this along the axis, and that way I can construct a continuous variable that is smoothly there. So this m lambda is what I mean by a coarse-grained magnetization, or in general, a coarse-grained order parameter. And when I write it down, I write down the scale of coarse graining. That's the lambda. And everything that I do with it is going to depend on what that scale lambda is. And sometimes I'll remember to include it, and sometimes I won't. So, but just be aware that that needs to be specified. Now, the question that we want to ask is not how do I construct the coarse graining, because that's easy. I'm just defining some sliding window that I move along, and I just define a variable. The thing we really want to understand is if you go back and look at what's here on the left-hand side, so here we have everything is determined by the free energy. Here we have everything is determined by the Hamiltonian. That's the microscopic thing. And then the question is, what is the analog of the Helmholtz free energy? What is the analog of the Hamiltonian for this intermediate scale of description? So the question, I'll come to your question in a minute. The question is, what is the probability distribution or m lambda of r? And what we're looking for is an analog of the Hamiltonian. And so what we're going to be thinking of then is that if I ask you this question for the microscopic spins, the answer to that is the probability distribution is 1 over the partition function e to the minus beta times the Hamiltonian of the spins. You tell me what the spin configuration you want. I tell you what is the probability distribution of that from that formula here. That's the Boltzmann distribution. So now what we have is we have an intermediate level of description. So now I have a function m lambda of r, and I want to know what it satisfies. And the answer is it's going to be something, I'll call it e to the minus beta times something here, which is going to be m lambda of r. And our question is, how do we construct this object? So this object is called the Landau free energy. It's sometimes called the effective Hamiltonian. And because m, the degree of freedom that it governs, is a function of scale, then in principle, this L is also a function of the scale lambda. So that's the thing that we want to know. How do we construct it? All right, Andrew, you had a quick question?
Yeah, what was your differential in that integral for the magnetization?
What?
The in some lambda of r is equal to summation integral of
Right.
that mess. And
Yeah, so there's a big mess, and all I'm doing is I'm averaging. If you don't worry about the formula, all I'm doing is I'm averaging all the degrees of freedom within that range lambda, and then dividing by the number of degrees of freedom in that range.
it was a d n sub j r sub j. What is that?
I'm summing. Yeah, it's not very clear. I'm summing over all the spin variables, and if for those spin variables, I'm choosing the point r and then seeing which spin variables are within a distance lambda, and I'm weighting them by a Gaussian factor, and then adding those things up.
I mean conceptually.
Right. Can I move on, and I'll discuss it with you afterwards if you don't understand the formula. All right. So then, why is this useful? Suppose we answer this question, then what that means is it's useful because I can say that e to the minus f over kbt is then equal to, well, we know over here it's equal to the trace over the spins of e to the minus beta times the Hamiltonian of the spins. And now what I've told you that in this middle, we have e to the minus beta times L lambda, m lambda of r. So I have that, and now I have to know what is the trace. So I'm just going to write it down as trace of m lambda, like that. And what we know that this notation means, this means sum over all possible microscopic spin configurations. And so this thing means sum over all possible smooth continuous functions. And we're going to need to know how to do that. And so that is the thing that is called a functional integral. And I'm not going to tell you now how to do that in detail, but one thing I'm going to make a comment on that's going to help us figure out how to translate that into a mathematical formula is we know that m lambda of r is coarse-grained on the scale of lambda. And so what that means is that it contains no spatial structure on scales which are less than lambda, because I've averaged over those. And so what that means is that if I compute the Fourier components of m lambda, so let me write it down. So that means the Fourier components of m lambda of k, I'm going to put a hat there so you know it's a Fourier transform. We're going to know that those are going to equal 0 if k, the magnitude of k, is much greater than, or just greater than, 2 pi over lambda. So in other words, by averaging over small distances, so up to the scale lambda, that means that this smooth function, the one I drew on the previous page, so you can see on the left-hand panel, that smooth function is smooth on the scale of lambda, so it has no Fourier components with an appreciable value for k greater than 2 pi over lambda. And that's how, so that gives you a clue that the way we can construct this functional integral is by doing integration over Fourier components. So what we will do is that means that we can give meaning to the functional integral by saying that it's the following. We take the Fourier transform of these components, so I get a complex number. The real part, I take the imaginary part. Then I take the product over all values of k, which are less than 2 pi over lambda. Those are the long distance parts, and then I integrate over that. And so that is the thing that defines a functional integral. It's a multiple integral over the Fourier components. And if I have a finite volume, then the values of k that are allowed in the finite volume are a discrete set of k. And so this is a huge multiple dimensional integral, but it's one that you can calculate. So we will talk later about how to compute that, but that is the basic idea of how we give meaning to this functional integral, this trace over my coarse-grained degrees of freedom. Okay, now let me talk a little bit about when this description applies. So that's the comment about functional integration. Now I want to talk about how useful is this? How useful is this coarse-grained description? And we know that the answer is, well, we are coarse-graining on a scale which is larger than the lattice spacing, larger than lattice spacing, but still smaller than the system size. And we know that to do statistical mechanics in the first place, we have to take the thermodynamic limit. So we know that we have to take the limit L goes to infinity for phase transitions in any case, the thermodynamic limit. So we need we want to make this range. We want to make this range as big as possible. And the nice thing is that when we are near a critical point, we know that lambda is less than or of order the correlation length. And this correlation length is going as T minus Tc over Tc to the power minus nu as T tends to Tc. And so that means that we have the condition A should be much less than lambda should be much less than the correlation length should be much less than L as L goes to infinity. And so what that means is this range is a huge range of scales. As we get closer and closer to a critical point. So this coarse graining is just another way of saying that the regions over which the system behave, the degrees of freedom behave as one variable, those increase as you get closer and closer to the critical temperature. And so that is a very good thing for us because it means that this description becomes very useful. Okay, so that's so what we've talked about now is the benefits of this description, but we haven't talked about how to construct it. So the next thing is how to construct this L. And I call it L because we call it the Landau free energy or Landau free energy density. It was first written down by Landau in the 1930s. He didn't really understand what he was writing down then. He had a very, very good idea, but I don't think at that time it was interpreted in the way that I'm telling you now. Later, after the normalization group came about, this sort of formula was written down. I think the first place that I ever saw it written down was in a paper by my postdoc advisor, Jim Langer, in 1974. So just after the normalization group had been invented, at that point it became clear that one should start looking at this level of description. Jim Langer was interested in looking at non-equilibrium phase transitions, and in fact worked out the theory of nucleation and spinel decomposition, all of the things that tell you about phase transition kinetics. That's what he became famous for. And so this level of description is the one that he understood. So I want to now talk about how to construct that. Probably won't finish it today. I'm going to show you. I'm going to show you a very simple argument for this. So let's talk about the strategy for doing it. So what we're going to do is in step one, we write down the mean field theory for a homogeneous system, meaning homogeneous in space. Then step two. So our mean field theory depends on the magnetization, M. Now what we've done is we've made M. We're going to make M go to M lambda of R. So you might think, okay, well, all I have to do is write down the mean field theory, the equation of state, just as I wrote it before, but now replace M by a spatially varying M. That's close, but it's not correct. The reason it's not correct is that we have to do a step 3, which is add additional term. That is the energy cost of having a spatial variation. So let me write this down for you in a very quick way. So we know that we know the equation of state for mean field theory is H over KBT is equal to MT plus M cubed. And I probably missed out a term here. I know there's a 3 in this somewhere. I know. Something like that. I don't know. I'm pretty sure I left out a factor in here. And then there's higher order terms. So that's what we already derived. So then you can ask, okay, what free energy does this correspond to? So the answer is, well, I take my free energy as a function of H and M. I differentiate it with respect to M and set it equal to 0, and that will give me the equation of state in equilibrium. So we assume that this coarse-grained free energy, this Landau free energy, is minimized in equilibrium. And so that will then tell you, just integrating this, that L of M, H, and T is going to equal to something, some constant of integration, which I'll write as T and M, minus M times H over KBT plus 1/2 T M squared plus 1/4 M to the 4th. And I'm pretty sure there's factors. I don't know. I think I'm going to take out that factor of 3 because it'll confuse some of you. So let's just sort it like this. Okay, so basically the functional form of this is going to be a quadratic in M and quartic in M. And when you did and T is going to come in over here. And when you did homework 1 and you used the 10-second theory to construct the free energy, this is what you did in that homework. Okay, so now step 2, and this is all I'm going to have time to do today. So step 2 is, now I'm going to take L of M and promote it to L of M lambda of R. And so we're going to get L of M lambda of R is equal to some L naught. And then I'm now going to integrate over space, because instead of just multiplying by space, I'm just going to integrate over a spatially varying thing. So it's going to look like this: integral d dr M of R H of R plus 1/2 T M of R squared plus 1/4 M of R to the 4th. And then I'm going to close those brackets. So this replaces taking this thing and multiplying it by the volume, taking this thing and multiplying it by the volume. Now, because M lambda is a function of R, to get the free energy for the whole system, we have to integrate over all regions of the system. And so we have that integral. So that's part of the way, but that's not the full story. Next week, we will add the last term, which is how we penalize variations in the order parameter in the magnetization over space. So that'll be what we'll finish up next time. Okay, so that's the end of today's lecture. So let me just turn off the recording.